Black holes ain't as black as they are painted. In my previous lecture, I left you on a cliffhanger, a paradox about the nature of black holes, the incredibly dense objects created by the collapse of stars. One theory suggested that black holes with identical qualities could be formed from an infinite number of different types of stars. Another suggested that the number of possible types could be finite. This is a problem of information. That is, the idea that every particle and every force in the universe contains an implicit answer to a yes no question. Because black holes have no hair, as the scientist John Wheeler put in, one can't tell from the outside what is inside a black hole, apart from its mass, state of rotation, and electric charge. This means that a black hole contains a lot of information that is hidden from the outside world. If the amount of information hidden inside a black hole depends on the size of a black hole, one would expect from general principles that the black hole would have a temperature and would glow like a piece of hot metal. But that was impossible because, as everyone knew, nothing could get out of a black hole, or so it was thought. This paradox persisted until early in 1974 when I was investigating what the behavior of matter in the vicinity of a black hole would be, according to quantum mechanics. To my great surprise, I found that the black hole seemed to emit particles at a steady rate. Like everyone else at that time, I accepted that the dictum that a black hole could not emit anything. I therefore put quite a lot of effort into trying to get rid of this embarrassing effect. But the more I thought about it, the more it refused to go away. So that in the end, I had to accept it. What finally convinced me it was a real physical process was that the wavelengths of the outgoing particles were precisely thermal. My calculations predicted that a black hole creates and emits particles and radiation just as if it were an ordinary hot body, with a temperature that is proportional to its surface gravity and inversely proportional to its mass. Since that time, the mathematical evidence that black holes emit thermal radiation has been confirmed by a number of other people taking various different approaches. One way to understand these emissions is as follows. Quantum mechanics implies that the whole of a space is filled with pairs of virtual particles and antiparticles, which are constantly materializing in pairs, separating and then coming together again and annihilating each other. These particles are called virtual because, unlike real particles, they cannot be observed directly with a particle detector. In their indirect effects can nonetheless be measured, and their existence has been confirmed by a small shift called the Lamb shift, which they produce in the level of light spectrum energy emitted by excited hydrogen atoms. Now, in the presence of a black hole, one member of a particle of a pair of virtual particles may fail into a black hole, leaving the other member without the partner necessary for mutual annihilation. The 4-second particle or antiparticle may fall into the black hole after its partner, but it may also escape to infinity, where it appears to be radiation emitted by the black hole. A black hole of the mass of the sun would leak particles at such a slow rate that the process would be impossible to detect. However, there could be much smaller mini black holes with the mass of, say, a mountain. A mountain sized black hole would give off X ray radiation and gamma rays at a rate of about 10 million megawatts, enough to power the entire world's electricity supply. It wouldn't be easy, however, to harness a mini black hole. You couldn't help it in a power station because it would drop through the floor and end up at the center of the earth. If we had such a black hole, about only way to keep hold of it would be to have it in the orbit around the earth. People have searched for mini black holes of this mass, but so far have found have not found any. This is a pity because if they had, I would have got a Nobel Prize. Another possibility, however, is that we might be able to create micro black holes in the extra dimensions of spacetime. According to some theories, the universe we experience is just a four-dimensional surface in a 10 or 11-dimensional space. The movie Interstellar gives some idea of what this would be like. We wouldn't see the extra dimensions because light wouldn't propagate through them, but only through the four dimensions of our universe. Gravity, however, would affect the extra dimensions and would be much stronger there than in our universe. This would make it much easier for a little black hole to form in the extra dimensions. It might be possible to observe this at the LHC, the Large Hadron Collider, at CERN in Switzerland. This consists of a circular tunnel 27 kilometers long. Two beams of particles travel round this tunnel in opposite directions and are made to collide. Some of the collisions might create black holes. These would radiate particles in a pattern that would be easy to recognize. So, I might get a Nobel Prize after all. As particles escape from a black hole, the hole will lose mass and shrink. This will increase the rate of emissions of particles. Eventually, the black hole will lose all its mass and disappear. What then happens to all the particles and unlucky astronauts that fell into the black hole? They can't just re emerge when a black hole disappears. It seems that the information about what fell in is lost, apart from the total amount of mass, the amount of rotation, and the electric charge. But if information is lost, this raises a serious problem that strikes at the heart of our understanding of science. For more than 200 years, we have believed in scientific determinism. That is, the laws of science determine the evolution of the universe. This principle was formulated by Pierre Simon Laplace, who said that if we know the state of the universe at one time, the laws of science will determine it at all future and past times. Napoleon is said to have asked Laplace how God fitted into this picture, and Laplace to have replied, Sire, I have not needed that hypothesis. I don't think that Laplace was claiming that God didn't exist, just that he doesn't intervene to break the laws of science. That must be the position of every scientist. A scientific law is not a scientific law if it only holds when some supernatural being decides to let things run or not intervene. In Laplace's determinism, one needed to know the positions and speeds of all particles at one time in order to predict the future. But we need also to take into account the uncertainty principle articulated by Walter Heisenberg in 1923, which lies at the heart of quantum mechanics. This holds that more accurately you know the positions of particles, the less accurately you can know their speeds, and vice versa. In other words, you can't know both the positions and the speeds accurately. How then can you predict the future accurately? The answer is that although one can't predict the positions and speeds separately, one can predict what is called the quantum state. This is something from which both positions and speeds can be calculated to a certain degree of accuracy. We would still expect the universe to be deterministic in the sense that if we knew the quantum state of the universe at one time, the laws of science should enable us to predict it at any other time. If information were lost in black holes, we wouldn't be able to predict the future because a black hole could emit any collection of particles. It could emit a working television set or a leather bound volume of complete works of Shakespeare, though the chance of such exotic emissions is very small. It might seem that it wouldn't matter very much if we couldn't predict what comes out of black holes. There aren't there aren't any black holes near us, but it is a matter of principle. If determinism, the predictability of the universe, breaks down with black holes, it could break down in other situations. Even worse, if determinism breaks down, mhm, even worse, if determinism breaks down, we can't be sure of our past history either. The history books and our memories could just be illusions. It is the past that tells us who we are. Without it, we lose our identity. It was therefore very important to determine whether information really was lost in black holes or whether, in principle, it could be recovered. Many scientists felt that information should not be lost, but no one could suggest a mechanism by which it could be preserved. The arguments went on for years. Finally, I found what I think is the answer. It depends on the idea of Richard Feynman that instead of one single history, there are many different possible histories, each with its own probability. In this case, there are two kinds of history. In one, there is a black hole into which particles can fall. In the other, there is no black hole. The point is that from the outside, one can't be certain whether there is a black hole or not. So there is always a chance that there isn't a black hole. This, this possibility is enough to preserve the information, but the information is not returned in a very useful form. It is like burning an encyclopedia. Information is not lost if you keep all the smoke and ashes, but it is difficult to read. The scientist Kip Thorne and I had a bet with another physicist, John Preskill, that information would be lost in black holes. When I discovered how information could be preserved, I conceded the bet. I gave John Preskill an encyclopedia. Maybe I should have just given him the ashes. Currently, I am working with my Cambridge colleague, Malcolm Perry and Andrew Strominger from Harvard on a new theory based on a mathematical idea called super translations, with the aim of explaining the mechanism by which information is returned out of a black hole. According to our theory, the information is encoded on the horizon of the black hole. Watch this space. What does this tell us about whether it is possibly possible to fall into a black hole and come out in another universe? The existence of alternate histories with and without black holes suggests this might be possible. The hole would need to be large, and if it were rotating, It might have a passage to another universe, but you couldn't come back to our universe. So although I am keen to a space flight, I am not getting to try that. I am not going to try that. My message here then is that black holes aren't as black as they are painted. They are not eternal prisons once envisaged. Things can get out of a black hole, both in this universe and possibly to another. So if you feel you are in a black hole, don't give up. There is a way out. It is a very interesting way to explain about the black holes and its like probable reality. So this was a quite interesting story, and about this book has come to an end. It's a really very small book, and for someone who is really interested in black holes, must read it. They might get some insights about how Stephen Hawking thought and made hypotheses about the black holes. So this is a very great book. I won't say a beginner's guide, but definitely has a lot of information about black holes. So do check this book out. I will put the link in the description for this book. You can purchase this. This is a cheap book and really interesting to read. You will get a lot of idea about black holes after reading this. I think there is some more content to this book. It is not related to the questions or the main content of the book, but some like preface or the conclusions. So I might not be reading that in the video, but I'll read it myself and will encourage you to buy this book and read it yourself. So thank you very much for staying in, and we'll now see you in the next book, reading the next book. Yeah, but same thing. So thank you very much for joining in, and we'll see you next time. Till then, subscribe to the channel, share these videos to your friends who are really interested in space and black hole kind of stuff. They would really enjoy it. So we'll see you in the next one. Thank you so much.